Hello YouTube and welcome to What the Math. In today's video we're going to be discussing what we've discussed last week, and this is of course planetary alignments. Now we're going to be doing a little bit of math today, and today I'm going to try to explain to you how planetary alignments are calculated and give you an idea on how you can actually calculate the next planetary alignment yourself. So let's actually start with the basic math behind planetary alignments. So here's our sun in the middle, and then we have a planet right here, and let's put another planet somewhere over here, and let's put another planet over here. Now this would be an example of an alignment, so you have everything in one line, and this is something that you would call planetary alignment. But that's not the only way to align planets. They can also be aligned in this way. Here is another planet. This is our green planet. Let's just actually say this is Mercury. This right here is Venus, and this right here is Mars. So they don't have to be aligned with the sun, they can also be aligned by themselves just like this. So this is an example of another alignment, and here we have something a little bit different. So there's actually quite a lot of possibilities for these alignments. They can be this way, they can be that way, and really the only similarity between these alignments is the line itself. So in other words, they have the same slope. If you remember algebra from grade 8 or whenever you did algebra, this is where we have to calculate the slope of m. So in other words, if we were to actually draw a coordinate plane right here, and I hope I'm not bringing back some scary memories, but this is essentially what this is all about. You have to try to calculate where the slopes of these points are essentially the same. So for example, for these 3 points we can calculate 3 of the slopes, and what we're looking for is something that would be, so let's just say this is point x1 y1, this is point x2 y2, and this is point x3 y3. So we can kind of summarize it as this. So a slope of line number 1, and slope is of course found by looking at the change in y-axis, or also known as rise, over the change of x-axis, which is known as run. So here that would be point y2 minus point y1 divided by point x2 minus point x1, and it should equal to the other slope. So these two slopes have to be equal. Let's just make them red here. So this slope right here should also be equal to this green slope right here. And this will align the 3 planets that we have right here. Now here's a more clear picture of what's going on here. So we have 3 planets aligned together, and what we need to find out is basically, well, we need several values here to make this a little bit easier. First of all, we need to actually find these points, and for this you actually have to use a little bit of trigonometry. So for example, to find this point, and let's just call this point x1. So to find x1, what we have to do is we actually have to look at this length. And if you remember trigonometry, this is actually a right triangle right here. So we're looking for the cosine of this angle right here. So in other words, we can rewrite this. Let's just say this is the radius of the orbit of this particular planet, and let's call it r1. So this is r1. This is the distance from the sun. So to find the point x, the value for point x, we can write this as r1 times cosine of this angle. Now we're going to call this angle omega 1t. What does that mean? Well, omega is the speed in terms of radians. So in other words, this is how fast the object is moving on this circle. Now circles can be divided into radians, and here omega represents radians per second. So in other words, it's sort of like this speed along the circle. And t is of course time. So t is time it takes to cover a certain distance. So if this is point x1, then to find point y1 we have to do the same, but this time use sine of the same angle. So in other words, to find x1, y1 for every single point along this circle, we're basically multiplying by the radius from the sun, or the radius of orbit from the sun. Or in case of Earth, it's simply that would be simply 1 astronomical unit, And here we then are multiplying by cosine of this angle or by sine of this angle to find the y value. Now I'm going to post a page for this particular calculation so you can take a look at it, because it's actually a little bit more complex than that. But basically, here are the 3 points, and here's how you calculate them. And what you're doing essentially is finding the slope. So here's the slope calculation, and if you rewrite this, if you actually try to essentially use the same denominator and same numerator, so you multiply this side by x2 minus x1, and you multiply this side by x3 minus x2, you will get this beautiful formula, and all of this equals to 0. And now all we're doing is we're rewriting this in terms of sines and omegas and t's. So basically, we are going to have something that looks like this. Now, this looks really complex and really scary, but it's really not that complex or scary, because all we're doing here is we're multiplying the first radius by the second radius. And here it's you can actually express this as a ratio to radius of Earth. So for example, if radius of Earth is 1, then radius of, let's just say, Mercury would be 0.3 something. Now then it's multiplied by sine of the angle 1 minus, or angle 2 minus angle 1 multiplied by time, and then it's all added to the second part. So here it's second radius, third radius, second angle, third angle, and finally third planetary radius and first planetary radius. And altogether, this has to give you basically 0. This has to equal to 0. When it's 0, that's when all 3 slopes are equal, and that's when all 3 planets will be aligned. Now, there's actually an even easier way of rewriting this, where you can actually convert this to even numbers. And you'll only have one variable, specifically t. So we're going to rewrite this again. And if you want to see how it's done in more detail, it's actually in this page I just showed you, and it's also in the description below. So this we're going to rewrite as the following function. So this first part, and I'm talking about this part right here, becomes this. So it's sine, bracket, 1 over r2 to the power of 3 over 2 minus 1 over r1 to the power of 3 over 2. Then multiplied by t, and all of this divided by r3. Now, remember, r1, r2, and r3 are just numbers, so you can actually convert these into numbers, and you'll only have some kind of a number here multiplied by t, which is going to be our variable. All of this is going to be added 2 times, so there's going to be another one here, and then another one right here. So the actual formula looks something like this. So here you go. This is what it looks like, and all of this equals to 0. Now, there's an explanation for why we can rewrite this. If you want to read this, it's in the website that I provided. But what we're going to do is we're actually going to try to graph this, and we're going to use various values of r. So if you actually go to NASA's website, and there's a website I provided in the link as well, it shows you distance from the sun for every single planet, including Pluto, which is no longer a planet. So here it shows you, in comparison to Earth, what is the actual distance of other objects. So for Venus it's 0.723, for Mercury it's 0.387, and for Mars it's 1.52, and so on and so forth, until this right here, I believe, is Neptune, and it's 30.05. This is Pluto. We're not going to do Pluto. We're only going to concern ourselves with everything up to the 8th planet. So these numbers can be written down in this formula as well, and we're going to be using something called Desmos graphing calculator, which is a free calculator you can find online at desmos.com, to basically calculate these. And so here's what we're going to do. I've already actually done the first one, and so the first one looks like this. This is what we can write this as. So this is the Venus, this is here Mercury, this is Earth, or this is 1, and we're going to add these sine functions and basically graph it to get a shape that looks kind of like this. You can kind of see what this is what it looks like, and it basically assumes that the first time, or at 0 years, we have our first alignment. So this is what alignment looks like, and this is what we're going to be looking for. This is in years as well, and you can kind of see that every maybe 1.5 years, or it's actually not very cyclical, it's always different. There is a very brief, very brief alignment, but it's so brief that you may not even notice it. But then after approximately, let's see, how many is it? I think it's something like 40 years. Let's see if we can find it. there is going to be another alignment coming up. So here we go. This is, I think, the first one after about 50 years. There's an alignment that's going to last for a few weeks, maybe even a month. So this is what we're looking for. This is the type of an alignment we're looking for. All of the other ones are just sort of really quick alignments. They're not really interesting, but every 50-ish years, or actually there's another one here, maybe another one coming up soon. I think there's another one right here. So all of these are actually what we would call prolonged alignments, and these are the alignments we're kind of interested in because that's what we just had a few weeks ago in 2015, and this is why people got so excited. Here's actually a really good one. After about 117 years, there's a really long alignment right here. Now this is for 3 planets, and specifically we're talking about Venus, Mercury, and Earth. So as you can see, it's not very common. It's actually not as common as you would think. And so let's actually do this for another 3 planets, and specifically we're going to add another one here, and this time it's going to be Mars and Jupiter and Earth. So I'm going to add another function, and I've already added this already. So basically we're replacing these numbers with numbers for Jupiter and Mars, and this is from NASA website. So I'm going to add it, and now it's going to give us a green function. So what we're looking for this time is an alignment of 2 of these functions at the 0 line. In other words, something like this. So you can see here they start all aligned, then after about a year and a half they're still kind of aligned-ish, but after this, look at that. It becomes less and less common. So there's maybe one quick alignment right here after 10 years, and after that it's going to be quite a while before we see another one. So okay, there's one at 33 years, but so far no really prolonged alignments at all. Okay, maybe here, maybe after 46 years, but that's not perfectly aligned and not as good as we actually want it to be. So it will actually be quite a really long time before we even see anything as what we basically see at 0 for Jupiter, Mars, Venus, Mercury, and Earth. So there's really nothing here. Okay, maybe this actually. This is probably the closest we'll get, and this is after 130 years. So they're not perfectly aligned, but they're quite in the same sort of region of space, and so this is what I think you would call alignment. All right, so that's only 5 planets. Is it 5? 6 planets? 5 planets. And here's the next one. So this is, I believe, Saturn and Uranus, and we're going to add those 2, and they're going to give us a blue line that has even higher sort of episodes. Basically, it doesn't come back to 0 as often, and you can imagine this is going to take us forever to find another intersection. So I don't even think there's going to be one for quite a while. And obviously, if we add the last planet, which of course is Neptune, this here is Neptune, along with Earth and Uranus, it's going to be quite difficult to find any points of intersection. I've actually tried to make it a little bit easier by including a 0 line so I can actually see where they intersect. But you know what? You can try this yourself. It's going to take you maybe a little bit to enter the actual formulas, but once you do, it's kind of fun to try to discover when is it going to actually align. And even after maybe hundreds and hundreds of years, I think this is probably the closest, 130. But even after hundreds of years, I kind of tried to scroll down to a few thousands even. I could not locate a single one where all of the lines, all of these colors would actually intersect. So there would be maybe something like this after 180 years where they're sort of in the same vicinity, but they're not really aligned. And if you keep going and going and going, you'll get a few of these really kind of close encounters, but I haven't seen a single perfect alignment yet. So chances are it might either take thousands and millions of years, or you'll just get, this is probably the closest. After 375 years, this is probably the closest we'll get. There's a few of these where they'll be in the same region of space, but nothing more than that. So when will this actually occur? When is actually the closest we'll have all 8 planets sort of in the same vicinity that you could maybe call alignment? So I guess after 375 years here. Well, according to a few websites, there's actually a date for it. It's in 2492. So let me just show you what this would look like. Here's the picture. Basically, we have Mercury, Venus, Saturn, Mars, Neptune, and Uranus all in the same sort of region of space, but definitely not a perfect line. So this is the closest we'll see, and only after about, what is this, like 450 years, 480 years, So not anytime soon, and I'm pretty sure all of us will be dead by then. And before that, the closest was in 1128, so 1128, and this is what it looks like. So a lot of these planets are kind of aligned-ish, but not really perfectly positioned in a line. So a perfect alignment where they're all in the same line is really difficult to get, and it would require quite a lot of browsing on Desmos to actually discover this perfect alignment. Although instead of actually scrolling on Desmos and trying to find this manually, you could also do this mathematically by doing the following. This is actually also on the website I just posted. And what you could do is this. So in Desmos, what you're going to do is you're going to write a new function. And so for every one of those complex functions, and let's just call them f of x for 1, 2, and 3, these are 3 planets, you're going to basically square it. In other words, this is what I'm talking about. This is f of x. I'm going to write this as f of x, and this whole function is now going to be squared, then added to this function squared, then added to this function squared, and finally added to this final function squared. This is what I wrote right here. In other words, I'm going to rewrite these as one general function, and the reason why we're squaring it is that because we don't actually want to have any signs in there. So what you're going to have is this is that complex function for Mercury, Venus, and Earth squared. This right here is same thing for Earth, Mars, and Jupiter squared. This right here is Earth, Saturn, and Uranus squared, and this right here is Earth, Uranus, and Neptune squared. So all of these together will give us a function that looks like this. And this is the function that you're going to be getting here. So what you're looking at here is the combination of all of the planetary interactions. And here we're looking at, of course, these zeros, but we're looking for a prolonged zero, not a very quick one. So I think after maybe 2.5 years here, there's sort of one that's sort of prolonged, but not really. There's one after 13 years, but once again, it's sort of close, but not really. And after this, for a long time, there's not going to be anything. So after the first linear planetary alignment, there's really nothing for the next hundreds of years. We're going to try to find at least one here where they're going to be touching the zero, but unfortunately so far there is nothing. But basically this is a combination of all of these functions together plotted as one and squared just to make it even more extreme, just to basically make it more accurate. So as you can see, there's nothing so far. And there we go. After 376 and 378 years, there's a few very brief linear alignments. Basically, this is the closest we'll get. After about 378 years, you'll get something that may be called a planetary alignment, but it's not really prolonged and it's not really that precise. And the one after that is after almost 2,000 years. There's one at 1921, and there's one at 1925, and so on and so forth. So basically, it will take almost 2,000 years for yet another alignment afterwards. So in other words, it does take quite a lot of time, and it's quite unpredictable. It's not really cyclical. There's no real patterns here. And so in order for you to actually find all 8 planet alignments, you'll need to look at the graph and you'll need to find the intersection with the zero here. Now, hopefully this was kind of clear and made sense to you. So what I've used here is Desmos. I've also used the website I'm posting in the description below that gives you the actual formula for calculation. And you can do this yourself. You can do this even more precisely by taking each of the planets individually. So you can take Mercury, Venus, and Earth. Then the second triplet should be Venus, Earth, and Mars. Third triplet would be Earth, Mars, and Jupiter, and so on and so forth until the last one where you have Saturn, Uranus, and Neptune. So basically, if you had 6 of these functions and then each of them you would calculate using the formula I showed you before and then square each of them and add them up, this would be a little bit more accurate, but also possibly give you even less intersections with zero. So this is how you would use math to calculate these particular complex intersections and linear alignments. Anyway, so basically this is how you can try to calculate alignments, and I think it's a little bit easier if you're just working with 3 or 4 planets, but if you'd like to find more than 3 or 4 planets, this is essentially what you would have to do. It's not a very easy process, but some people actually enjoy this. Hopefully this was clear, and hopefully now you know how to calculate planetary alignments using mathematics and using this particular formula that shows you the alignment of planets in relation to radius and also time. Alright, thank you guys for watching. Hopefully you enjoyed this video, and hopefully you enjoyed the explosions and the collisions in the background. Game you later, and see you in the next video. Bye bye. And please don't forget to like this video and to subscribe if you still haven't. There's more videos coming with math, science, space, and everything else. Bye bye.